Operators provide us with a way to interrogate a wave function to learn about its properties or the properties of a physical state that it represents. And there are actually going to be two postulates that we need to cover that talk about this sort of measurement capacity. So the first of these indicates that if we make a measurement of an observable property that corresponds to some operator, it must result in an eigenvalue of that operator. So let me remind you of what we learned earlier about eigenvalue equations, in particular operator eigenvalue equations. Okay, they have the form that looks something like this. We have an operator A, and it's operating on some function. Let's call it psi. And if psi is an eigenfunction of that operator A, then it will result in a multiple of that wave function, where A is the eigenvalue. Now, it's important, again, to clarify that A is an eigenvalue of the operator that corresponds to psi, which is an eigenfunction. Okay, you will not get a neat and tidy relationship like this for every function, only for particular functions that happen to satisfy this eigenvalue relationship. All right. So let's, though, talk about the fact that most operators have more than one eigenfunction and more than one eigenvalue. So in order to keep track of those, what we often do is we give them a little label, typically a subscript. And so I might write, for example, that this operator A operating on one of its eigenfunctions, which I'll label with a subscript n, is going to give one of perhaps many eigenvalues a sub n multiplied by that same eigenfunction. All right, now what we can say about this particular relationship is that for each of these eigenfunctions, phi sub n, they result in one eigenvalue. So in other words, if you have an eigenfunction, it's got an eigenvalue. It doesn't have more than one eigenvalue. It has just one eigenvalue. But at the same time, I may have more than one of these eigenfunctions that have the same eigenvalue. And this is something that we saw in the particle in the 3D box, results into a quality we call degeneracy. All right, this doesn't always happen, but it can happen. So it's important to understand that if I know an eigenfunction, I will only get one eigenvalue when I plug it into this eigenvalue equation. But if I happen to know an eigenvalue, it's possible that it corresponds to more than one eigenfunction. All right, so about this labeling, let's look at a good example for how this works. And what we typically find is that the most common example is naturally the Schrödinger equation, and we see something like this, where the Hamiltonian is operating on an eigenfunction, and it gives one of the energy values for that Hamiltonian. Most systems have more than one possible energy value. So this is just the example of the Schrödinger equation. So for example, the particle in a box had particular energy levels that were labeled by this subscript n. All right, now what we have learned, at least in the initial stages here, is that if we have bound systems, these tend to have a countable set of discrete values for E. Just as I've written it here. But if I have an unbound system, in this particular case, I have a continuous set of energy values. Okay, I already mentioned that one of the examples of the bound case is the particle in a box. What about the unbound case? Well, we've also seen an example of this. The free particle is an example of an unbound system. And in that case, many different energies can satisfy the Schrödinger equation and be the results of a measurement of the energy in this case. So it's important to understand the Hamiltonian is the quantum operator that measures the energy of a system. And so the eigenvalues will be those energies, and those allowed energies will depend upon whether the system is bound or not bound. All right, now, what if the state of a system is not an eigenfunction? Okay, this is all written very specifically for eigenfunctions, but the state of a system doesn't necessarily have to be an eigenfunction of the Hamiltonian. What if it is something else? Well, what we can do is we can often express the state of a system. So let's say that this is my state of the system. I can actually express this as a linear combination of various eigenstates of the Hamiltonian. So, for example, it could be a linear combination of a couple of eigenstates. I'll add 3 of these, and by eigenstate I really mean eigenfunction. Okay, so I could have something like this, where the actual state of my system is a combination of several different eigenfunctions, where, remember, my notation in this case is meant to imply that for this subscript j, I'm going to get the jth energy level. Okay, so the first energy level corresponds to this eigenfunction, the second to that, the third to that. So I don't have a really detailed answer that I'm going to get when I measure this. All right, so what do I get? All right, well, I need to go to the next postulate to sort of clarify what that is. If the state of a system is a normalized wave function but not necessarily an eigenfunction, then when we measure some property, and I've left that property open as A here, not just the Hamiltonian, but when we measure that property, it's going to be an average of the possible eigenvalues of that operator. All right, so how might I express that? Well, I've shown you an example where I had an eigenfunction, or a wave function, sorry, a system wave function that was simply a combination of 3 of the eigenfunctions of the Hamiltonian. So if I were to measure the Hamiltonian, measure the energy of this system, it's going to be some kind of average of these results. But each time I measure the system, I have to get an eigenvalue. Okay, that's the big distinction here. For a single measurement, I have to get an eigenvalue. But if I make a whole bunch of measurements and I've prepared the same state each time, I may get different eigenvalues if the state that I'm starting in, this psi, is not an eigenfunction of the Hamiltonian. So there's a way that we can write this down, and let me show that. We can write it down like this, and I'll explain the notation in just a moment. And we've seen some of this notation a little bit, I think. All right, if I construct this sort of integral, where this psi now represents the system wave function, and I'm integrating over my d tau, so you can see this as a multiple integral, as it probably is. This would represent the average value that I would measure in this case for this observable operator a hat. All right, so this A is not necessarily A1, A2, or A3, but some kind of weighted average of those. And it's weighted by the probabilities of finding myself in one of these eigenstates, if this corresponded to eigenvalues of A. Now, I want to close this by also telling you how this would be written using that special notation we've introduced. I could write this like this. Okay, and this is a little bit different than something I've shown you before, where I've inserted an operator in between these two, just as it is inserted here in the middle of this integral. So when I write something like this is what it means. It's an integral over all space of the operator sandwiched between the complex conjugate and the normal expression of the system wave function. All right, so this now corresponds to an average value for the measurement of this property A. All right, we'll see this in several examples in the lessons to come, so I think you'll get more and more comfortable with it, but it's important to know that this is defined via this postulate.